What the actual fuck is nuclear fusion? Well, today I'm going to explain the process behind it, how it works, what kind of elements it forms, and how quantum tunneling participates in it, and how it powers our sun, giving us life. So, let's begin. So, what is nuclear fusion? Well, nuclear fusion is two smaller nucleuses combining and forming a bigger atom, like two hydrogens combine into a helium, and two heliums combine into a beryllium, and two berylliums combine into oxygen. Now, it's easier said than done. And right now, I'll show you the process of it. Imagine you're a gigantic star. Now, you're a star and you have a lot of mass. And all of that mass around you causes a lot of gravitation. So you start pushing inward. You start collapsing into yourself. Now, when you're compressing, the atoms inside of you start compressing as well. So, taking closer into the look of the star that is collapsing, these two hydrogen atoms right here start coming closer and closer towards each other. But they don't touch or fuse because they're both positively charged protons. So they repel each other. But at some point, the gravity becomes so unbearable that they have to fuse. And doing so, fusion happens. Those two protons form a bigger nucleus. And this nucleus isn't just two protons like this. Instead, one of the protons switches into a neutron and releases a neutrino and a positron, which is the antimatter of an electron. Now, as you see here, we have a bigger nucleus. We have deuterium. And deuterium is the building block of the sun. During nuclear fusion, these two protons, when combining, they lose mass. And so the nucleus that comes after nuclear fusion, this one right here, weighs less than the two protons combined. So what does that mean? That means that mass has to be turned into energy. And because of E equals mc squared, that energy is a butt ton. So doing so, the star that was compressing because of its gravity force starts pushing back because of all of that energy released during nuclear fusion. And that becomes a balanced reaction, giving the star its shape. But scientists realize something crazy. Nuclear fusion has to have a certain amount of temperature. If a star simply isn't hot enough to cause nuclear fusion, then there's going to be no nuclear fusion. But stars still that aren't hot enough to cause nuclear fusion still produce fusion. But how does that work? Well, when these two protons become super hot, they start jiggling super fast back and forth. That's what temperature is, the average kinetic energy of atoms or molecules. So that now these protons right here are jiggling super fast. When jiggling, they hit each other, they fuse into the deuterium atom. But if the sun isn't hot enough, they can't jiggle fast enough or have enough kinetic energy to become fusion, to have a fusion. But they still do. Well, that's because of quantum tunneling. Now imagine a wall, and you're a particle, and you want to cross this wall. You can't cross this wall unless you break through it. But let's imagine this wall right here is unbreakable. So you physically cannot cross this barrier. But particles, like these protons, to fuse into one another somehow do. And that's because of quantum mechanics. All particles, all subatomic particles, like protons, are waves. So they, instead of being a particle, it's a wave like this. And this wave predicts the probability of a proton being there. So the highest point, which is right here, has the highest probability of a proton being there. And if a and the smallest probability is around here. So there's a tiny probability of a proton being there. So let's imagine the proton is moving forward into the barrier. So let's imagine that. You can see the proton has a high probability of not being on the other side of the wall. But when we keep drawing the graph, you see there is a tiny probability of this proton being on the outside of the wall. But this probability is so tiny that it basically doesn't happen. But luckily, in a gigantic star, there are billions and trillions of these tiny collisions happening. Amount of those collisions happening beat the odds of quantum tunneling, allowing nuclear fusion. And because of quantum tunneling, stars that aren't big enough to have proton to proton nuclear fusion still have nuclear fusion, even though they are not hot enough. Okay, but nuclear fusion doesn't just stop at deuterium, it continues forward. Then the graph looks something like this. We have the deuterium atom right here. Then after that, this deuterium atom fuses with another hydrogen atom. And this gives us gamma radiation and a helium atom. Now, this helium atom also weighs less than all three of these subatomic particles combined, which means it has to release energy, and it releases some of that energy as gamma radiation and as just regular energy powering the sun. Now, this doesn't stop here. Two more of these helium atoms, helium-3 atoms, as you can call them, cause another fusion. And when they fuse into something, they fuse into a stable noble gas called helium-4. And helium-4 is inert. As we see, there are 4 protons in total and 2 neutrons. So where did the other 2? Well, those other 2 protons simply just split off and do that whole nuclear fusion process again. And those helium-4 atoms that we saw earlier continue fusion, and they continue combining, and they combine and combine and combine and combine and combine until they reach iron. Now, as I said before, during nuclear fusion, it releases energy because of the equation E equals mc squared. So the product of nuclear fusion usually weighs less than the 2 products that combined it into, which releases energy. But during nuclear fusion, when combining into iron, it actually weighs more. So iron takes away energy. So what does that mean? So let's draw our star again. Now, like imagine you're a star and you already lived for millions and millions and millions and millions, even billions of years. Now, you've been running out of hydrogen for a while now, and you have a shell right here. You've been expanding, and your shell right here is just full of inert helium. Whatever's inside this thread right here is just helium that can't fuse. It's inert. And inside is your iron core right here. This iron core is also inert, and it actually takes away energy. So you start compressing because of the gravity, and there's no energy pushing you out anymore. It's less. And because of that, the star keeps compressing and compressing and compressing and compressing until it collapses and either forms a black hole or a neutron star. Now, here's the problem. How do we have other elements heavier than iron? If the biggest nuclear fusion can make is iron, how do we have things like gold or uranium or tungsten or osmium or indium? How do we get those heavier elements? Well, it's simple. During the collapse of a gigantic star, there are things called a supernova, which means the star collapses so violently it explodes outwards. Doing so, that explosion is so violent and so fast in that split second that crazy amount of nuclear fusion happens and gives us heavy elements like lead, bismuth, palladium, indium, iodine, bromine, and all those other atoms. Still, we have heavier elements like gold and neodymium and uranium and other those heavy elements. Where do those happen? Well, as I said before, when they collapse, they either become a black hole or a neutron star. And neutron stars are super dense, which means they have a gigantic gravity field. So when two neutron stars are next to each other, they start attracting towards each other super hard. And when they combine into a bigger neutron star or into a black hole, they explode as well like a star. And that explosion is millions of times more violent than a regular supernova. And that gives us the heavier elements like gold. And most of the gold that you're wearing or that you have or you see comes from these violent explosions. To summarize, nuclear fusion is this: smaller atoms combine into bigger atoms in stars until they reach iron. Once they reach iron, the star can't be powered anymore, and it collapses inward. Doing so, it causes a violent explosion called a supernova. That supernova gives us heavier elements like iodine, bromine, and silver. But we still have heavier elements like gold. But those only form in super powerful universal experiences, like when two neutron stars combine. And that event is so powerful, it causes bigger nucleuses to form into even heavier atoms, like gold. So that is our today's video. And if you enjoyed it for today, make sure to follow. Make sure to like, make sure to join my Discord in my bio, and please, for the love of God, join my Patreon, support my future projects, and gain epic perks. And as always, I love you guys consensually, and I hope you have a great rest of your day.
Please join my Patreon. Please join my Patreon.